Okay, let's start. I'm going to review the questions you asked regarding study guide. The first one is question 2. We have a graph here. It's the solid fat content of some lipids, and we need to label each of the curves. So we need to make a prediction using our knowledge about solid fat content and melting behavior of the lipids. So solid fat content is the percentage of lipid that is solid at a particular temperature. Now let's read that graph. Let's look at lipid E. So what do you see? Here we have like around 10% solid at 0 degrees Celsius. Now we go here, it's like 15 degree, we have 0% solid. 20 is the same, 0, and it goes like 0 at these temperatures. Okay, let's write here. So 0% solid at room temperature, right? So that means this lipid is liquid at room temperature because it has 0% solid. So let's look at these lipids. So E should be olive oil, right? Because it's liquid at room temperature. That means this lipid is highly unsaturated. So E should be olive oil. Let's look at D. So what do we see? Seems like it has a broad solid fat content profile. It is broad because it has different solid fat contents at different temperatures. It is not a sharp curve, it's decreasing gradually. And when it becomes liquid, at what temperature? It's like 35, 36. We can say this lipid melts close to body temperature. Or just maybe at around body temperature. Now we cannot make a prediction with just this information, so let's move on. Let's look at C. It has broad solid fat content profile too. And melts, here you see like over 40 degrees Celsius. So what about B? So when we compare with D and C, it has sharper solid fat content profile. So what about the melting point? It's the same with D. It melts at around body temperature. Let's look at A. So as you see, A has the sharpest profile. It goes like almost straight and then suddenly falls to 0. Okay, let's try it. What's the melting point? So maybe over 65 degrees Celsius. So it has the highest melting point. Okay, now try to guess which one is which. Since A has the highest melting point, it should be highly saturated. In contrast to olive oil, right? It has the lowest melting point. And we said it has sharpest profile, so it's composed of pure triacylglycerols. So now here we see 3-stearine. So composed of 3-stearic acid. (18 carbon, 0 double bond. Long chain hydrocarbon and highly saturated. Then A must be the 3-stearine. Okay, let's continue. So which lipids melts at body temperature? Butter and cocoa butter, right? You know, cocoa butter found in chocolates. So which one is it which? How we are going to decide? With triacylglycerol composition. So it has 3 major triacylglycerols. So this is palmitic, oleic, palmitic, stearic, oleic, stearic. So I will just write here. Palmitic, oleic, stearic. You know, oleic is unsaturated. It has only one double bond. So cocoa butter contains a high proportion of saturated fats, but mainly composed of these 3 triacylglycerols. And butter contains more than 3. So we saw that B has a sharper profile. So B must be cocoa butter. Because it has 3 major triacylglycerols. Then D will be butter. because it has more than three acylglycerols, so it will have broad profile, because every 3-acylglycerols has different melting point. Okay, now automatically this becomes palm oil. And it makes sense, we know that palm oil is high in saturated fats. Okay, the next question is 4. What is the importance of cooling rate during crystallization of lipids? Cooling rate is important during crystallization. Why? Because it affects the formation of polymorphic forms. So which one is better, slow cooling or fast cooling? The slow cooling is better. It results in well-ordered, more stable structures. Why? Because of efficient packing. Due to this efficient packing, good packing. Okay, in order to have a good packing, you need to cool the 3-acylglycerols slowly so that they will have enough time to form a well-ordered, more stable structures. Okay, let's look at question 5. Compare the polymetric forms of fats illustrated below in terms of stability, density, and melting points. So we have alpha, beta prime, and beta. So these are the cross-sectional shapes of the packed structures. So this one is another illustration. It's easier to understand. It's easier to see the order of the structure. Alpha has the least stable structure and beta has the best stable structure. So they go like that in terms of stability, density, and melting point. Again, the critical point is packing. Okay, you can easily see with this second illustration. Remember, these black balls are carbons. In the alpha form, 3-acylglycerol chains are packed in the hexagonal shape and the chains are rotating. So due to this rotation, the chains cannot pack well. Therefore, the distance between the chains is big, and alpha is the least stable form. In beta prime, the chains are not rotating. That's why they are packed better than alpha. So in beta form, the distance between the 3-acylglycerol chains is shorter than beta prime and alpha. And this is the best packing structure among these three. Okay, that's it. The next question is question 9. Fill in the blank. Remember, there are two types of hydrogenation, partial hydrogenation and fully hydrogenation. So during hydrogenation, we saturate double bonds with hydrogen. If we do complete fully hydrogenation, all double bonds will be converted into single bonds. They will be saturated. But if we do partial hydrogenations, some bonds will stay unsaturated, right? But it will also cause formation of trans fatty acids. The configuration will change. That's the major limitation of partial hydrogenation. So we don't have that problem with fully hydrogenated fats. So that's the answer. Let's see the other question. And you ask question 12. Why is singlet oxygen more potent than triplet oxygen in lipid oxidation? Okay. Remember, they differ in their electron shells. One is like that. And the other one is like that. Electron spins are different. So they differ in their chemical properties due to these differences. So let's write. Singlet oxygen is highly reactive. Okay. More electrophilic. Than triplet oxygen. So reacts with electrons in double bonds. I will say easily. Okay, that's why it's more potent than triplet oxygen in lipid oxidation. It can easily abstract hydrogen from double bonds. Okay, let's see the last two questions. How does degree of saturation affect formation of fatty acid radicals? First, I'm going to answer, then I'm going to explain. So I will write like that. The ease of formation of fatty acid radicals increases with increasing unsaturation. So unsaturated fats oxidize easily. But why? Okay, I'm going to write here. So first remember that slide. So when we increase the double bond, reaction rate increases. Oxidation becomes faster. Also, there's another sentence here. As the bond dissociation energy decreases, lipid oxidation becomes faster. So what does that mean? Let's see that. So we have carbon-carbon. And unsaturated. Now we have carbon double bond. Fatty acid radicals are formed by abstracting hydrogens. Let's see these bonds. So which one will be easier to remove? This one will be easier. If a carbon atom is adjacent to an electron-rich double bond, then this carbon-hydrogen bond becomes weaker because of this electron-rich double bond. For example, the bond dissociation energy here, let's say 90 kilocalorie per mole. So then this becomes, let's say, 60 kilocalorie per mole. Okay, as we said before, as the bond dissociation energy of the carbon-hydrogen bond decreases, hydrogen abstraction, hydrogen removal becomes easier. So lipid oxidation will become faster. Okay, that's the reason. Unsaturated lipids are easily oxidized. Okay, let's see the last question. Describe the primary and secondary lipid oxidation products. So what are the primary lipid oxidation products? Lipid hydroperoxides. So they are initiated by the formation of fatty acid radicals. Remember, with hydrogen abstraction. Then these free radicals reacts with oxygen to form a peroxy radical. And this peroxy radical has high energy. So due to the high energy, of the radical, it can easily abstract hydrogen from the lipid molecule. So this is another lipid molecule forming lipid hydroperoxides. Which are the primary oxidation products. And this is the propagation. So oxidation might stop here with a termination step, depending on the oxidation conditions. Remember the lecture slides. The enzymes, ionizing radiation, the presence of transition metals, they accelerate the oxidation. So depending on the degree of oxidation, here, these lipid hydroperoxides decompose into secondary oxidation products. With beta-scission reaction. These secondary oxidation products are particularly dangerous and they contribute to a number of pathological dysfunctions of the human body, even cancers. They are responsible for sensory changes in food, negatively affect its taste and smell. Okay, that's it. You can answer the question briefly like that.